Last time we were together, we walked through a couple recursive algorithms, and I showed you how to calculate what they're doing by using a recursion table and a recursion tree. So I want this algorithm now, before we dive into it, this one causes more heartache when I do this activity in class than any other ones. What is the name of this algorithm? That's the name of the class. X. The algorithm's name is X. Okay, that's the name of the function, right? Now, I called it that because I don't want to tell you the name of it, because maybe it's a pattern you might recognize, maybe it's not. But I didn't, like if I called it factorial, right? Then you would know, oh, well, I know how to calculate factorial. So I want you to not know what it's going to do. So the function is called X. What I want you to do is walk through using a recursion tree. So let's take a look at what's a tree all about, right? That's throwing a couple people off. First of all, just general terms, a tree is made up of what we call a node or a vertex, or multiple nodes or multiple vertices, which can be represented with circles or squares or whatever shape you want to pick, right? And then you connect those trees, those nodes, I should say, with what's called an edge or just a simple line, right? So the question is, in this case, what goes in each little node of our tree? What goes in each vertex of our tree? So we're starting off here we're trying to solve what is x of 3, right? That is the name of our function right here. We just ran that, and it's going to run this block of code right here. So I'm trying to figure out, what is that? What is x of 3? Well, just manually look at it, and we can look inside the function here. Is 3, which is the n right here, is it equal to 1? It's not. So if it's not, then what's going to happen with that tree? It's going to do this block of code right here, right? So it's going to return n, which at the moment is 3, and then it's going to return x of n minus 1, which is x of 2, right? So that means that x of 3 is the same thing as 3 plus x of 2. Agreed? So another way to write x of 3 is that. That is identically, mathematically identical. Whatever that equates to will be exactly the same as that. Okay? That makes sense? Well, now we look at x of 2, and we're going to run x of 2 through our code, and we look and see, is x of 2, is 2 equal to 1, or is n equal to 1? The answer is no, so the else statement runs again, and we now know that the else statement is going to be n, which is 2, plus x of 2 minus 1, which is x of 1, right? So we can split up this x of 2 into two pieces, like that. Now we run x of 1, and we look at that, and in that case, n is 1, right? That's what's being passed in right here. And if n is equal to 1, we're supposed to return n, which is 1. So what does that tell us we know about x of 1? What is its value? X of 1's value is 1. So what is this value then? It's 3, right? Because it's 2 plus whatever the heck that is, and whatever the heck that is 1. Right? So we now know x of 1 is 1. You add those up together, you get 3. Well, we also were taught that this is exactly the same thing as this. Therefore, what is the value of x of 2? 3, right? Okay? So, therefore, what is the value of x of 3? Right? It's the total of those two together, and it's 6. Right? So, now I did that with a small number there, but these trees can get pretty complicated pretty quickly. Also notice I'm only returning n plus, n minus 1, or x of n minus 1. We could have had some other formula in there, times this plus that minus that, all kinds of stuff. But I just want to get a quick one so we can just see a very easy example of walking through a tree, okay? Next up, I want to walk through, there's our final answer. I want to walk through a table, a recursion table that, again, you already know the answer. You already know what the values are, but I want to make sure you understand how to use the table to figure out what it's going to be, okay? Are there any questions about the tree, though? All right? So this is the same formula, same everything, I'm pretty sure. Double check it before you write any numbers down. But this time we're going to use a recursion table. All right, so a table works the opposite of a tree. With a table, you start with what you know. With the tree, you start with the final x of whatever, right? The final, the thing you're calling, right? This is what you're calling. Your tree starts there. With a table, you start with what you know. So what is the only thing we know? We know what n of 1 is, or x of 1 is, right? We know that because we're told here. The only thing you'll ever know in a recursive function without actually running the code is the base case, or base cases, if there's more than one, right? So the whole point of a table is this. You're trying to figure out what is n of 1, or what is x of n, let me say that again. You're trying to figure out what is x of n when n is equal to 1, when n is equal to 2, when it's 3, when it's 4, when it's 5, and so on down the line until you hit that number right there that you're going for. Well, we only have 3, so we can stop right here, right? Well, we already know what the first one is, right? First one, we know that when n is 1, we know that x of n will also be 1. That's just the first line of the function. We already know that. So now we want to figure out what about when n is 2? Well, we know that when n is 2, it's not, this line won't run because it's not equal to 1. So we say whatever n is, 2, plus whatever x of 2 minus 1 is, which is 1. So those two numbers added together, okay, which is equal to 3, obviously. Now, don't get stuck in the trap that, oh, it'll always be this number plus that one every time I do a table. Well, no, it's going to be this number, that operation, that number, right? It'll be different with every function you're doing, okay? But in this case, we are just adding. So next up, when n is equal to 3, we do that operation again. We do n plus x of n minus 1. We get 6, okay? How do we feel about using those as tools to solve a recursive equation? We good? Okay? I heard someone say, oh, crap. Yeah. This is where it gets, this is why we care about this, all right? So this is a recursive algorithm, and this algorithm, if I pass in a and n, right, it will return a to the n power. What we want to do is prove that that is true for all, well, you can see it right there. Prove the following algorithm will return a to the n for all non-zero real numbers a and all non-negative integers n. And you can see that with the data types I chose here, right? Float a, and we're only allowing that to be non-zero, right? And then integer, non-negative whole integers. We want to prove that it will actually calculate that for every single possible combination of a and n. That's infinite, right? That's an infinite amount of numbers for a and an infinite amount of numbers for n. Agreed? But yet we can, using mathematical induction, prove the truth of this recursive function here. So now the question is, do I pause the video and let you guys try to figure that out?
Yes.
Good.
No.
Nathan, what's your vote? I know what your other half would say.
I don't like it.
She would say yes. She likes to work through the problems. So she's going to be our absentee vote here. So I'm going to let you guys think through it for just a couple minutes. Let me give you a couple of hints though. Remember, with we've been looking at recursive functions here. These are recursive functions, and much like a recursive function, a mathematical induction is very much like a recursive function. We start with a base case. We have to prove the base case, right? So how do you prove a base case? You plug in the numbers to the function and see what it returns. That's easy, okay? How do you do a recursive case? Well, we assume that if it's true for k, it's also true for k plus 1, right? Well, what is k and k plus 1 in this context? That's the puzzle I'm going to leave for you guys to work on for a couple of minutes. We're going to walk through part of it together. I'm going to lead you down the path a little bit, and then I want to have you guys continue on. So while we're recording, we're going to walk through part of it, and then I'll pause it again and let you kind of see if you can pick up where it was. All right, so always when you're doing a mathematical induction proof, you have to start with a base case. And the idea of the base case is to plug in some actual real number, or numbers depending on what kind of function you have, and see if it mathematically comes out the way it's supposed to. So in this particular case, let me get like a sort of a quasi whiteboard going here. The function's called power. So I need to figure out power of a comma n. That's what you're supposed to pass in, right? Well, I'm going to leave a as it is because a is too hard to pick a number, because a goes from negative infinity to positive infinity except for 0, right? It's every other possible number, right? So we're going to leave a alone, but what happens if I pass, what's the lowest number I can have for n? 0. Based on the set that we're describing here, it's all non-negative integers, right? 0 is not negative. It's also not positive. It's just not negative too, right? Okay, so it's non-negative. So it is the lowest one you can have. So if I say the power of a0, well, let's look at what happens in our function. I pass in a 0 right here. Well, what's this function told to do? Just ignore this error trap right here. The function here looks and says, is it 0? Is n equal to 0? Well, if it is, return 1. That means that this line right here does not get run, right? It just returns 1. So if I put power a comma 0, I will get 1. Is that true? Is that mathematically accurate? Yes, it is, because anything to the 0th power is always 1. Okay, good. So there, that's our base case, done. We plugged in an actual number, we have our base case. And now I've talked to you before how I like to sometimes prove more than one base case, but you can't really do that here, can you? No, you can't. Okay, you could, you could plug in a and n equals 1, but at that point I don't want to get super circular here. I want to actually have a hard answer that we know is correct. Then we're going to do our mathematical induction step to prove the rest of it, okay? All right, so now, get back on the slide here. With the inductive step, we always assume that it's true for k, right? So, and then the rest of that goes, if it's true for k, therefore it will be true for k plus 1. So we start by assuming this to be true. Because if it's not true, then I don't care if it's true for k plus 1 either, right? All we care about is if this is true. So why am I putting k here, not here? Yeah, we can't, there's not a whole lot we can do with a, so it's just a variable that's going to have to stay at a. So we're trying to prove that any number that I put here, any number that goes here, that this will calculate out. So the proof is actually only asking us that very thing, to prove that this will work for any number that we put there, okay, within the bounds of the scope of the number. So we start with 0, which is our lowest possible number, then we throw in some number k, and we see if it works with k plus 1. We assume it will work with k because that's the rule of the inductive proof, all right? So we can see that if this is true, would you agree that that is true? Or is there anybody who doesn't understand that piece of it? Like, why are we assuming it's true? Why is the left thing mean the right thing is true? Is there any part of that that's unclear? We okay with that? Okay, so if you buy that if power a comma k is equal to a to the kth power, then the next step is proving that it is true for a to the k plus 1, a comma k plus 1. I'm going to leave that as the hint, and so hopefully that'll get you in the right direction. We'll pause the video for a few more minutes. All right, so we've done our base case. We know it's true. It works. We made our assumption that the k case will work, right? The a to the power of k will work. That if I plug in a and k here, that this will happen. Again, we assume this is true, right? That is a part of the inductive hypothesis or the mathematical induction proof, right? Our inductive hypothesis is that that's true. When it's true, will k plus 1 be true? That's what we need to figure out, right? So we just basically need to do a direct proof of that. We need to prove that if I plug this in, is it going to end up looking like that? Okay? So how do we do that? Well, let's take baby steps here, all right? First of all, if we look at the code, it tells us that the power, which is the name of a function, a to the k plus 1 is equal to what? It tells us it's equal to a, whatever a is, times the power of a to n minus 1. Well, what is n minus 1 if that's our variable? It's k, right? K plus 1 minus 1 is just k. Agreed? So then that means that according to the code, that if I plug this in, this is what we'll calculate. That's what we'll compute, right? Agreed? Okay, now, we know this one already. We've seen that one before. That's our inductive hypothesis right there. So what can I do with that? I can substitute an a to the k for that because that's our assumption that that's true, right? So if I do that, then we'll get, per the inductive hypothesis, that's the same thing, right? That equals that. Right, now I left the a stranded there for just a minute. We'll come back to that. Okay. So in other words, this, which equals this, is the same thing as that. That is all 100% true with our inductive hypothesis power a to a comma k equaling a to the k. If that's true, this is all true so far. Okay. Now what can we do? Yeah, use your exponent rules, right? Right, so per the rules of exponents, a times a to the k is equal to a times k to the plus 1. In other words, there's an imaginary 1 right here, right? A to the 1. And so whenever you have two where the base is the same and you're multiplying, you're raising it to some power and some power and you're multiplying them together, it will end up being the same thing as whatever that power is plus that power, right? So I know that was a little messy there, but that is mathematically the same as that. Make sense? So, per mathematical induction, the algorithm is correct. That's all we had to do was prove that if I ran this through the function, that would be the output. And as we see, mathematically, based on what's happening here, because that's just a math operation, the computer can't not do math correctly unless there's something like seriously wrong with the computer, right? Or the operating system. So assuming that that's not an issue, which we should always assume that, then this will actually put out the correct answer. So in the event that this holds true, this will also hold true. Therefore, it is true for all cases. We proved it for a base case, we proved it for k, and we proved it that if, or we didn't prove it for k, we proved that if it's true for k, it will be true for k plus 1. That's it, okay? Most of you, I think, got pretty close there, and I stopped and gave you some hints along the way. Hopefully that helped. How do we feel about that overall? This stuff is tricky business, right? But why do we care about this? Why does this, why would I ever have to do this?
To prove something.
Yes, it's very vague, but it's true. I'm trying to teach my daughter that when she says, I lost her Barbie doll, it's either in the living room or somewhere else. And she'll say that, and I'm like, that narrows it down to the entire known universe. I'm trying to teach her that everything is either in my living room or somewhere else, right? Anyway, so yes, it's to prove something that is true. Here's the thing. This is a simple algorithm, right? It's a very simple, just calculating the power of some number to some power that you're passing in. It's very simple. Algorithms get much more complex. We can almost just sort of, eyeball it, if you will, and look at it and go, yeah, it's right. Can almost do that, right? But if it's bigger and it's more complex and there are more steps and it's recursive and there's lots of other crazy things going on here, then a proof by mathematical induction can be very useful to prove that the algorithm actually works. So you prove it mathematically, which all told probably took us about 15, 20 minutes maybe. You prove it mathematically, then you have confidence that, okay, now I'm willing to throw some data at it and see if I break my computer, right? So before you throw some real data at it, you just get a text file or loop it through a database and try, millions of combinations and see if it runs efficiently and it's getting correct answers. You've proven that it will always work. Now the next step is make it more efficient, right? Which is what 2420 is all about, making your algorithms efficient. But this proves that it works without having to run an infinite set of numbers on it, which is something you can't do. All right, how do we feel about this? We good? Any questions about it?